So an Algebra 1 student asked me how to solve this linear system of equations, and I thought this was interesting because they wanted to do it by solving by graphing, and we're actually not going to solve it by graphing. What we're actually going to do is take a look at what each of these systems and solutions represent. So you have a unique solution, you could have infinitely many solutions in the middle, you could have no solution. And these are the systems that they relate to. It could be a consistent system, like for unique and infinitely many solutions, or it's an inconsistent system, has no solution. And then we're going to talk about linear independence and what it means to be linearly independent or linearly dependent, as in the case of infinitely many solutions. And then we can get into span and planes. But first, we're just going to take a look at how to solve this, maybe just using substitution. So I'll leave that on the side. And as we take a look at substitution, what we would need to do is I'm going to just take this one and solve for y. So it just seems to be the cleanest for right now. I'm definitely going to end up with a weird fraction over 8. This is going to be negative 2y equals 8 minus 3x. And I'm going to just divide by negative 2. This is going to be negative 4 plus 3 over 2 times x. You could also write it like this, 3x over 2. I think that's probably easier. Now what I'm going to do is I'm going to take this guy and I'm going to substitute y back in. It takes a while to do this. 5x, now I'm going to solve for x, substituting y. And here I'm going to substitute y in. And y is going to be negative 4 plus 3x over 2 equals 7. And now I can solve for x because I have only the x variables in here. So 5x, this is actually going to be, after I distribute the 3 in here, this is going to be negative 12 plus 9 over 2 times x equals 7. Great. So now you can see that we distributed the 3 in here, and we're going to solve for x. This is going to be 5x. Basically, what we should probably do, actually, is get a common denominator for these two. So I'm going to do that real quick, and we can move the 12 to the other side. This is going to be 19. This is going to be 9 over 2x. And we need a 2 in the denominator. So this is going to be 10 over 2 plus 9 over 2x. And so this is going to be 19 over 2x equals 19. And you can see that, obviously, I'm taking kind of the long way. If you could already see this in your head, you could solve it. But I'm going to just show every step just in case you don't know how to get there. So I'm going to divide by 19 over 2 on both sides. Dividing by that is actually the same as 19 over 2 is the same as multiplying by the reciprocal. So we could write it like this. Obviously, the 19s cancel out, and you're just left with x over 2, x equals 2. Great. So now I've got x equals 2. Now I can use the original equation, either one really. I can use the original equation, and I'm going to solve for y now, because I need both of them. So this is 3x. Now I'm going to plug x in here. Divide by negative 2 is equal to negative 1. So I've got x equals 2 and y equals negative 1. And it's not terribly difficult. This is probably the easier way to do it rather than the row operations right off the bat. And you can see that we actually found the unique solution. So this is a unique solution. The system is consistent. If we look over here to the right, it is a consistent system. It is linearly independent. And what does that mean? That means that I cannot write the second or the first row as a linear combination of one or the other. I cannot get this line from this line. So we say that they are independent from each other. They are linearly independent, and obviously they're both on a line. So that makes total sense. And when we say that this is a unique solution, we mean to say, and this is the part that a lot of people forget, including myself, that this is an intersection. This is the solution. I mean, not really, but representing a solution, an intersection. And so if we have infinitely many solutions, what does that look like? Well, they're all on the same line. And so we can say that they are collinear, that I can get one from the other, that they are linearly dependent, and we'll take a look at that next. And when we have no solution, what does that mean? They're linearly independent, but they don't touch each other. How does that work? And it's because they never touch each other. They're actually parallel. And so they'll never intersect and you'll never get a unique solution. Therefore, it's no solution, it's linear independent, and it's an inconsistent system because you can't get from one to the other. And so when you have something that is linearly dependent, you can also think of it as being on an axis. If we draw this thing again, a plane, now we can say that all of these are on this plane. And so if I drew another, let's call it line or vector, I can never get from one to the other. I can never get back onto this plane from this vector without doing some math. It is linearly independent. And you can see there's an angle here. I can never get back on there. And that's what it means to be linearly independent. If we look at our example again, what could make this have infinitely many solutions? Let's try it. And I can tell you right off the bat, and I'm going to replace this with 10x minus 6y is 14. And you might say, well, how did I know that this was going to make an infinitely many solution right away? Well, let's think about it. Let's try to do some row operations. And by doing row operations, we can see that I actually can do something to get this. I actually can cancel this out. So what I would need to do is -2 times row 1 plus row 2 would give me the new row 2. And then I'm just going to rewrite the first row. 5x plus 3y equals 7. And now I'm going to multiply this -2, just like we have -2 times the first row plus the second row. So -2 times 5x is going to be -10x. And then I'm going to add that. And then I'm going to do it for the 3y. So this is, and now I'm going to do it for the 7. Well, you might say now I have a row of all zeros. Well, that's exactly right. And that's exactly what it means to be linearly dependent. Because I can get this multiple. You see that 5x, 6 and 3, 7 and 14, these are scalar row multiples. It just means I can get one from the other very easily. So it is linearly dependent. And it's pretty obvious in this case, but it won't always be so obvious. And so now we know that these equations are on a certain plane, which is very, now we're getting somewhere. Now we can see what infinitely many solutions looks like and what a unique solution looks like. Now maybe we should just quickly review no solution. Okay, I've got a new system of equations for us. Let's try to give this a go. And we can just try to solve for this. Let's start with the second equation, x plus y equals 7. And let's solve for y. So put this into the other equation and solve for x. So we're going to have 3x, insert y, and I'm going to solve for x. Put over on the right-hand side that we have y equals 7x. And I recommend doing this so you're not lost in the equation like we are somewhere up here where I have to now hunt for the equations, put them in one spot. 3x plus 3 times, we have to distribute now, plus 21 equals 4. Now, this is interesting because we have 21 equals 4. Is this true? It's not true. That's the problem. So this actually has no solution because 21 obviously is never equal to 4. When you have something false, this is false, this is not a true statement, this means that it can never happen. And even if we wrote it differently, let's write this a little differently, because what happens if I didn't see this right away? What happens if I actually did this? 3x minus 3x, and I move the 21 to the other side. So we have 17. That is the point. You actually have 0x. This also means no solution. So now that you have a little bit more experience, what I'd like to do is to review a couple of these problems using linear algebra instead of solving for these variables like we did down here. And so how I'm going to do that, now we know that this is a unique solution, right? So now we know that this should be linearly independent, meaning that we cannot get one of these equations from the other. So what does a linear combination mean? It literally means we are adding and multiplying by some scalar, and all we've done is now use these variables as a linear combination to form a linear combination. And you can call these x and y in this case. And now we can rewrite this even more incredibly as times is going to give me, this is pretty crazy because now we can solve this a lot more easily. And by the way, to get this back, we're not going to go straight across. You would take this row and multiply it by this column. And the same thing goes for here to get this original system back. We're not going to go into that. That's assuming you understand a little bit about vector operation and matrix operations. So you can go over that in your own time. But we can rewrite this system of equations as this. And once we have this, we can actually even go further and say that this is 5, 3. And now we can do what's called Gauss-Jordan elimination. And it's basically, it takes the reduced row echelon form, and it basically does these elementary row operations for us. So let's go ahead and look what that would look like. I'm going to use this program, and this is basically like MATLAB. It's an octave interpreter as the matrix, and that's how you do it. You separate each row by a semicolon, and you can use the comma or not, but if you don't, you have to use a space. If I do A, and it's going to process this for me, and you can see that this gives me this matrix, which is really cool. Just to save some time, what we can do is we can call REF, which is reduced row echelon form, and how we do Gauss-Jordan elimination, basically how we solve this system of linear equations. We're going to get, and the thing is, I actually didn't put the solution in here. We're going to go 5, 3, 7, and we're going to go straight across. And now I'm going to do reduce row echelon form. By the way, we can also rewrite this as now one or two matrices. Now we have what's called a partition matrix, where this partition just kind of acts as the equal sign. Now doing this reduced row echelon form, you can see that my matrix actually went from 5, 3, 7, 3, negative 2, 8 to 1, 0, 2, 0, 1, negative 1. If I do the same thing that I did to get it here, let me move this out of the way. I can actually now rewrite this as x. Likewise, I can say this is 0x, but actually we have that x equals 2 and y equals negative 1. And look, we only had to do these operations in this reduced row echelon form, which would require some row operations in this case, I get it. But we used octave or MATLAB or another thing, or even a calculator to calculate this for us. And we didn't have to do all of this by hand, which now makes it a lot easier. And just seeing by this matrix, I can tell you that this is a unique solution. This is true, and this doesn't have a row of all zeros. So if we look at this one now, we can easily get there. And we get there, we can start from here. I'm not going to redo the whole problem. I'm going to just take this and put it into this matrix form like we did over here. And we do that by just taking the coefficients. And where we see the equal sign, we're going to put this partition. And there you go. There's basically your augmented matrix. We can see that there is a row of all zeros. This is a homogeneous system right here, at least this part of it. And so that this means that now we can make this row up from another row. And so we can say that, therefore, this is linearly, and we already did, but we're going to say it again now that we have this is linearly dependent. And yes, this has the trivial and non-trivial solutions. So this is trivial, particular. This is trivial and non-trivial. There you go. So with that being said, we're actually now ready for the real question. And I took you through all this algebra just to show you that we can use these matrices as a way to represent linear combinations and find linear dependence a lot faster using the reduced row echelon form and Gauss-Jordan elimination. So we don't have to do these row operations. I mean, in this case, I think I would end up with 7 over 3 or 5 at some point when doing these row operations, and this is really going to trip you up. Even doing the graphing method for this one will get you some fractions that you'll have to plug back in. Even right here, we had a fraction. I mean, this is one's pretty easy to solve, and it ended up working out and canceling it out for us, but it's not always going to be clean. And so when you use this, it's going to be pretty good. And even better, if you can see that this is a scalar multiple of one another, or a row multiple in this case of one another, that's going to really help you to get to the type of system it is quickly, and to say, yep, that's infinite many solutions without even solving. So this can say, we can say that this has unique and trivial infinitely many solutions. For something like this, we can not really see that it's no solution right off the bat, but at least we're getting somewhere. And we can see that once we get to the bottom, it does have no solution. So let's move on to the problem. There we go. So to solve this, what we're actually going to do is, first, we can convince ourselves that this is going to work, because this could be 1, 2, 2, 4. In a matrix, we have A, X, so we have some X vector, X2, all the way down to Xn, equals B. So this is -2, -4. And what this means is that what this implies is that we have C1 times this vector, to make this a linear combination, C1, X1, and so on and so forth. And what this means is that we can now form an augmented matrix. So we don't have to go through okay, there's going to be one, we can do this, but we don't have to. Matrix, which is going to give us. Now, to solve this, what we're going to do is use octave, and what we want to do is reduce row echelon form. So this is basically the form that gets us to the solution every single time, if there is one. And to do this, we're going to just rename A 1, 2, -2, 2, 2, -4. And remember, if you don't use the spaces, you absolutely have to use the commas. I just prefer the commas. It's a little bit faster. And I always check the matrix 1, 2, -2, 2, 4, -4. So that comes out to be is just the row of zeros, as you can see. We already know that this is going to be homogeneous. We already solved for this whole row. So now we need to solve for the leading ones, because the leading ones will tell us the solution. And so we can rewrite this as the vector x is going to be equal to, a good reminder, the leading ones are going to give you x1 equals, and it doesn't really matter which one you do. I always kind of just put that this is going to be equal to -2, and so we know that x2 is equal to 0 in this case. And the way that we represent that, we know that this is in the domain, x is in the domain of all real numbers. So I can use basically any number, and we're going to call this little r, just to represent any real number. And now I can begin to rewrite this, because x2 can be equal to 0, it can be equal to 1, it's equal to r in this case. And so we can rewrite this as -2 minus 2r, because we just did this by substitution, and x2 is just going to be equal to r. That's what this implies. Splitting this apart, basically what we did before, the reason why I showed you that, is now we can split this up into two vectors. And we can say that this is -2, 0, plus, as a linear combination, r, -2 and 1. And so the solution to the linear system, ax equals b, in the form x equals, where this is the solution to the homogeneous system, and this is the solution to the inhomogeneous system, which we already know that, respectively, this and this. And we show that because there's not strictly the trivial solution, and there's not strictly the all zero solution, the zero vector. So in the form of this, we have x equals, so maybe we put it therefore, since this is the big finale, equals. So that's how you solve for a linear solution using the homogeneous solution and the inhomogeneous solution as this guideline. So now that we've reviewed the different types of outcome systems and we've reviewed the inhomogeneous and homogeneous solutions, we reviewed span, which covers linear independence. Now we can start to look at things like basis, which are related to both span and linear independence, and we could start looking at different transformations and coordinates. That'll be in the next video. So now that we've reviewed the different types of outcome systems and we've reviewed the inhomogeneous and homogeneous solutions, we reviewed span, which covers linear independence. Now we can start to look at things like basis, which are related to both span and linear independence, and we could start looking at different transformations and coordinates. That'll be in the next video.